This lesson is about electrostatic energy and capacitance. Let's first consider the energy required to build a system of two charges. This can be written as the product of the electrostatic potential due to charge number 1 times the value of the charge number 2. And the electrostatic potential is the potential produced by charge number 1 at the position of charge number 2. So we have this expression for this energy. Now, as a general expression to build a given charge distribution in space, we can have several different formulas. Particularly, we can write this energy as 1/2 the volume integral of the volumetric charge density rho omega times the potential in space that is produced by rho omega itself. Other equivalent expression consider instead of potential and charge the fields D, the flux density, and the electric fields, and the expression is shown here. We can substitute in place of D its relationship with E so that we have an expression for E only. All these are equivalent and corresponds to the electrostatic energy stored in space due to a given charge distribution. Of course, the term that is into this integral can be considered as an energy density, and therefore the electrostatic energy density can be written as 1/2 D dot E or 1/2 epsilon E square magnitude. Now, let's consider two conductors, 1 and 2, and let's apply a voltage difference between these two. As a result of the application of this voltage difference, some charge is drained. Initially, these two conductors are neutral. Some charge is drained from one conductor to the other, so that as a result of the application of this voltage difference, there is a net charge appearing on one of the two conductors, let's say capital Q, and minus capital Q on the other conductor. Okay, the capacitance of this two-conductor system is the ratio between the charge on the positive conductor divided by the voltage difference. So we can express this by this ratio also in terms of fields, and specifically we can write the fields, the D field because the charge is related to the flux of the field, and the voltage in terms of the line integral of the electric field, so that we can write also an expression for capacitance that take into account only the fields, the D and the E field. The capacitance is also linked to the electrostatic energy because, let's say, is a quantity that relates to the capability of the system to store electrostatic energy. And in particular, we can write that electrostatic energy due to a system of two conductors for which a given capacitance has been computed can be written as 1/2 the capacitance times the square of the voltage, or, if you prefer, 1/2 the square of the charge on the positive conductor divided by the capacitance itself. The unit of measurement for the capacitance is the farad. So the typical example we do when we speak of capacitance is that of capacitors made of parallel plates, in which there are two, as you see, plates, conductive plates, that are set at a given voltage difference and on which there is a storage of charge. The two charges are equal and opposite, and we can define for this very simply the value of the capacitance, because when the two plates are placed very close to each other, we can neglect the presence of the fields outside the region between these two electrodes, these two plates, and we can consider that the field inside is constant. From this assumption, we can obtain a very simple expression for the capacitor, which is epsilon, if vacuum is present between these two electrons, epsilon naught, times the area of the plates, A, of a single plate, divided by the distance between the plates. This value of the capacitance is a good approximation for the true value in which there are other small effects that take place, such as fringing fields that are placed also slightly around the plates and not strictly confined in the region between the two plates. If we substitute vacuum with another material, a dielectric, the value of the capacitance increases by the permittivity, the relative permittivity of the dielectric, as shown by this expression, because this contributes to the storing of the charge. So we have In addition to the capacitance of two electrodes in 3D, two metallic bodies in 3D, we can also define a capacitance per unit length for an infinite length of conductors in space. Of course, if the two conductors have an infinite extent in length, the total capacitance is infinite, because when you apply voltage difference, there is an infinite amount of charge. But a unit of length corresponds to a finite amount of charge, and therefore this finite amount of charge can be divided by the voltage difference to define a capacitance per unit length. The expression with a similar consideration about the field that is placed between these two plates, as you see, that strip line, these two parallel plates. When we neglect fringing fields, the expression for the capacitance per unit length is very simple, is epsilon times the width divided by the spacing between these two conductors. So in this direction, we assume that this strip line has infinite length. If we replace the internal material with two different materials, epsilon 1 and epsilon 2, you can easily observe that these two correspond to two capacitances in parallel. So they are subject to the same voltage difference, and the charge on the two is the sum of on the two charges, on the charge on W1 and on the charge on W2. So that these two capacitances add, and we have that the total capacitance is the sum of the two. Very similarly, if we instead substitute the internal material with two materials with different epsilon r but placed stacked, like in this picture, in this case, this geometry corresponds to the series of two capacitance, and the formula for the series for the capacitance is shown here, so that the series of the capacitance corresponds to a total value of capacitance is less than either of the two. The capacitance per unit length of a two-wire system, of a two-wire lines, where we have this cylinder, this other cylinder, and we apply voltage difference between the two, can be obtained from the 2D expression of the potential. In fact, we have that the 2D expression can be written in the form of a logarithmic function, as we saw previously. If we replace the various parameters that we see here, the various distances, we have the distance between the two centers of the two conductors, which is d. We have these parameters r naught plus, r minus, r plus, and so forth. We substitute, we obtain finally an expression for the capacitor that is very simple. As you see, we have the final expression is shown here at the bottom of this slide, pi epsilon naught, which is the material between the two, therefore vacuum, divided by the natural logarithm of d, the distance between the two, divided by r, which is the radius of the two conductors, if the radius is the same for the two. If it's not the same, so we have r plus and r minus, we have this other expression in which the logarithm is d squared divided by the product r plus times r minus. For the case of a coaxial line, the capacitance per unit length can be obtained as usual by computing the voltage and the potential distribution, imposing a given potential distribution between the two electrodes, internal electrode, external electrode, and obtaining from this voltage distribution the charge on the positive conductors. The expression for the various integrals that we find in this computation is shown here, and you see as the output the value of the capacitance of the coaxial line. It's a very well-known line in telecommunication because it's a transmission line. We see what this means later on in the course, that is capable to transfer RF signals from two endpoints. For instance, for cable TV are made with coaxial cable. This coaxial cable has a capacitance that can be expressed in closed form in this way. If we replace partially the internal conductor with another material, we have that if the replacement is of this type, so we replace a portion, an angular portion of the coaxial with another material, we have the sum of two capacitances per unit length, as shown by this expression.